Here we look at some questions involving the Arrhenius equation. Here we've been asked to work out activation energy, and we've been given the rate constant, the temperature, and the Arrhenius constant. So in order to do this, we need to look at the Arrhenius equation, which again is an equation you do not need to remember, but it might be worthwhile you remembering it anyway. So we've got the Arrhenius equation, and now we need to rearrange this equation to get me activation energy. The first thing we really need to do is convert this into the log form of the Arrhenius equation, which is ln K equals ln A minus EA over RT. Now, if you're really good at maths, you could probably work out this procedure to convert the exponential form into the log form. If not, it may be a good idea again to just try and remember this log form here of the Arrhenius equation, because once you get this, it should be basic algebra to rearrange anything in this equation. So what we need to do is we need to get activation energy. The first thing we do is we add EA over RT to both sides, and that gives us ln K plus EA over RT. That is equal then to ln A. We then subtract ln K from both sides, and that gives us EA over RT equals to ln A minus ln K. And then we simply need to multiply both sides by RT. That then becomes EA equals ln A minus ln K RT. And if you like your maths, we can simplify this up a little bit, and we've got now my rearranged equation there to give me activation energy. Either of these equations are fine, they'll give you the same answer. Let's now plug the numbers in. So activation energy then is equal to, we said it's ln A over K, so it's ln, and A we've said is 9.5 times 10 to the 9 divided by, and K is 1.00 times 10 to the minus 5, and times by R, which is 8.31, times T, which is 300. I think when you do this log form, you should get a number around 34.5, maybe just under 34.5. So when you do this, you get an activation energy of 85977 joules per mole, and we've got quite a big number there, so we normally would convert that into kilojoules per mole, so we could divide that by 1,000. That gives us an activation energy of, to three significant figures, 86 kilojoules per mole. That would be my answer. Now I'm going to take a look at another calculation. We're going to take a look now at how to calculate the temperature. So we've got to calculate the temperature. We're given, again, the rate constant, the activation energy, and the Arrhenius constant. So if I want to work out T, it's one step away from what we've got here. So if we know then that EA is equal to ln A over K times RT, then all we need to do in order to get T is to divide both sides by ln A over K times R. So T then will be equal to EA divided by ln A over K times R. And that there is my rearranged equation there to get T. And if we plug the numbers in then, we would see that T is equal to, the activation energy is now 75,000. So we do have to remember that this is given in kilojoules per mole, but it should be in joules per mole when we put it into the Arrhenius equation. So we've now got ln of A, which is 9.5 times 10 to the 9. Over K, which is 1 times 10 to the minus 4. And that's multiplied then by 8.31. And when you plug that number into your sum into your calculator, you should get an answer of 280 Kelvin. And that there is your answer. So they've looked at two examples of how you can use the Arrhenius equation, one to work out activation energy and the other one to work out temperature.